பண்ணிட்டீங்கன்னா இது ஓடும். இப்போ நான் ஹைட் பண்ணிடுறேன். நான் வெளியில் நான் இங்கே தான் அப்புறம் நான் வெளியில் இருக்கேன்.
இப்போ
பேசி முடிச்சுட்டு
இப்போ ரெக்கார்டிங் ஓடுதா?
ரெக்கார்டிங் பண்ணி சார். நான் கட் பண்ணிடுறேன்.
ஓகே கட் பண்ணி.
நான் செல்ஃப் இன்ட்ரோ எடுத்துட்டு கட் பண்ணிட்டு
Okay. Hi everybody, this is Kumaran, Assistant Professor, Department of Mechanical Engineering, and I'm going to give a lecture on the topic mouse click learn program.
touch பண்ணிட்டு
இதில் போகுது ஆமா ஓகே
மறுபடியும் மறுபடியும்
Hi, I'm Kumaran, Assistant Professor, Department of Mechanical Engineering, and today we are going to see a lecture on engineering graphics and unified approach. This engineering graphics is nothing but it's called as language of engineers. It's called as language of engineers for the reason that many people from different part of the world, they have their own standards and they follow their own language. And in order to have a uniform understanding, the drawings are represented in a standard way. So that's why, and all these things have fundamentally some basic concepts. For example, the projection of any of the object as a fundamental principle. That's why we see an unified approach. Let's see the objectives and outcomes of this lecture. Upon completion of this lecture, students will be able to, number one, understand clearly the concepts of projection in drawing, the elements of projective geometry is basically a mathematical background, and the conventions and notations used, and to classify the projection, and to obtain orthographic multi-view projection of an object. Now let's see what is this fundamental elements. The fundamental element consider is point A. There is a point which is an object whose projection has to be obtained. You have an observer who wants to obtain the image of an object. The observer's horizon level, that is the eye level, is marked with this red dotted line, which is your horizon. The next one, you have the plane of projection, which is otherwise called as picture plane. So these three are the basic elements of the projection. You have an object whose image has to be obtained. You have an observer who is looking at an object to obtain the image of an object. The image of an object is obtained on the plane of projection or a picture plane. Now let's see the other things. The observer is standing on the ground and looking at the object. He casts a ray. The ray, which is an imaginary line which is drawn from the eye of an observer, which falls on an object and which pierces the plane of projection at some point. That piercing point is called as your projection, which is marked as A dash, which is one of the notation. That is, the object is labeled as a capital A and its image on the plane of projection as seen by an observer is marked as A dash. So A dash is nothing but the projection of an object, capital A, on the plane of projection as seen by an observer who is going to stand at a finite distance from the plane of projection as well as the object. Now let's consider another point B, which is labeled as capital B. The observer also looks at that object, so he casts a ray on that object and the ray pierces the plane of projection at a point B dash. So A dash is going to be the image of an object A on the plane of projection as seen by an observer, and B dash is an image of an object B as seen by an observer. Now consider the projection of a line. If there's a line connecting A and B in this case marked as vertical, but A and B need not be vertical, it could be of any fashion, then the image of the line AB, that is the image of the object line AB, can be obtained by joining the images or the projections of the endpoints A and B. So the projection of a line AB is obtained by joining the projections of the endpoints A dash and B dash as seen by an observer. So in this fashion, an object, say a planar object which contains say minimum 3 points, or a solid object that contains say more than 3 points, something like a tetrahedron, any object projection on a plane as seen by an observer can be realized using this method. So this you call as projection. Projection literally means to throw something. Here the observer throws rays of sight, or it could be even rays of light. Now here we have seen the projectors are the rays, and have shown in the animation that the rays are coming from the observer's eye and falling on the object and pierces the plane of projection. It can also be realized something like this, that the rays are coming from the object and it gets focused on the retina of the observer. Sometimes the observer can be replaced by the light source, so that the projection can be thought of as the shadow of an object as seen from a ray that is cast from the light source. So again I reiterate that the three basic elements are the object, the observer, and the plane of projection, and he obtains the projection of an object by casting a ray on the object that pierces the plane of projection, and thereby obtaining the projection. So this is the concept of projection. The next, let's see how to realize this in a three-dimensional plane. Now look at this. You have an object A, then you have a station point O, you have a picture plane or plane of projection. Now the observer casts a ray on the object, and the ray pierces the plane of projection at a point which is labeled as A dash, the piercing point, which is a projector. Next, there's an object B, which is behind the plane of projection. The observer casts a ray on the object capital B and obtains an image as B dash. Next one, there's an object C. So these are your point objects, point C. Then the observer casts another ray and obtains the piercing point as C dash. There's another point object D. The observer casts the ray and he obtains the piercing point as D dash. So piercing point is nothing but the point of intersection of the ray with the plane of projection, that you call it as the projection or the piercing point. Now if ABCD in the blue color is going to be the real object, that's going to be a square or a rectangle, then the image or the projection of the rectangle as seen by an observer at the station point O is obtained by joining all these projections in sequence. So here you can realize that AB, if it's going to be a line object, then A dash B dash is going to be the projection of that as seen by an observer. Similarly, the line BC, CD and DA, all these things can be thought of independently as lines, and together they form a planar object, a square or a rectangle. Now this is the concept. Now let's try to move this observer. Let's try to move this observer. So this is going to be your perspective projection. This is called as your perspective projection. Now let's have a different look. You have the ground line, then the plane of projection, then object, which is the object is going to be red in color. If the rays are going to be parallel to each other, and if the observer is going to be kept at infinity, then all these rays will travel to infinity. That is, if the observer is going to be at an infinite distance, then the rays that is cast from the observer's eye, it is going to be parallel to each other. So when they are going to be parallel to each other, you call that as parallel projection. So it's called as parallel projection because the projectors are parallel to each other. And when they are parallel to each other, and if it's made perpendicular to the plane of projection as indicated by the perpendicular symbols marked close to the plane of projection, and you will find that the size of the image is going to be the size of the object. They are going to be identical. That is, the size of the image or the projection of the line here is going to be same as the size of the object. So this is going to be the case of an orthographic projection. The word ortho means 90 degree and graphics means drawing. It's going to be a 90-degree drawing. That is, the projectors are going to be perpendicular to the plane of projection. Of course, this we will realize only when you're going to keep the observer at infinity, then the rays becomes parallel to each other. Look at this. There's an object A, a point object. Then there's a station point which is going to be at infinity to realize the parallel projection. You have the picture plane or the plane of projection. The observer from infinity casts a ray on the object and it pierces at the point A dash. Similarly, you have a point B. The observer at infinity is going to cast a ray on the object B, which pierces at B dash. And there's a point C, a point object C, and the observer casts a ray and obtains the image, which is nothing but the projection of the point capital C on the plane of projection, which is labeled as C dash, it's a piercing point. Then there's a point D behind the picture plane, and the observer casts a ray on the object and obtains a piercing point, which is nothing but the projection of the point D, which is labeled as D dash. If ABCD is going to be an object which is made out of lines AB, BC, CD and DA, then the image or the projection of the rectangular object is obtained by joining the projections of the endpoints of the respective lines AB, BC, CD and DA. Now here in this case, we will find that the projection A dash, B dash, C dash, D dash is going to be of the same size because the rectangular object is going to be parallel to the plane of projection. So these projectors which are drawn, which are parallel to each other, it may be perpendicular to the plane of projection, in which you call it as orthographic projection. It could be inclined to the plane of projection, in which case you call it as oblique projection. So this is a parallel projection. Now let's see about this concept of projection. The perspective projection, central projection or conical projection. Whatever we have seen as an observer was casting a ray which forms a cone. So that you call it as your conical projection. Because you have a center of vision, you call it as central projection. And because he is getting the view of every object, you call that as perspective projection. Perspective projection is classified under three categories. One is going to be your linear perspective, the next one is your aerial perspective, and the next one is going to be a parallel projection. In linear perspective, you have 1.2 perspective, 2-point perspective, and 3-point perspectives. These point perspectives are nothing but the number of vanishing points. If you have only one point at which all the receding edges vanish, you call that as 1-point perspective. And if you have two vanishing points, you call that as 2-point perspective. If all the three principal axes they vanish at three different points, you call that as 3-point perspective. An aerial perspective is nothing but you are going to get an aerial picture of an object. And in parallel projection, we have already seen parallel projection is going to be a special case of a perspective projection in which the observer is kept at infinity. In this parallel projection, you classify this as oblique projection and orthographic projection. As I told you, oblique projection is one in which the projectors are going to be inclined to the plane of projection, and orthographic projection is one in which the parallel projectors are perpendicular to the plane of projection. The word ortho means it's going to be perpendicular or normal, and graphic means drawing. A drawing with projectors normal to the or perpendicular to the plane of projection. And in oblique projection, you have cabinet projection, a cavalier projection, clinographic projection, and shades and shadows. Widely used oblique projection is going to be your cabinet and cavalier. A cabinet projection is one in which the length of the object is going to be the same, whereas in case of a cavalier projection, which is mostly widely used in those days for making military drawings, that's why it's called as the cavalier projection. The length is foreshortened to half of its original length. Now in orthographic, you have axonometric projections and multi-view projection. Axonometric projections are nothing but axis-based projections, and multi-view projections are nothing but you take multi-views of an object in order to describe an object. We'll come back to that multi-view projections. What is it? And in axis-based projections, you have three kinds. That is isometric projections, dimetric projections, and trimetric projection. An isometric projection in which you have three principal axes of the solids. If the object is tilted in such a way that the three principal axes of the solid appears to be equally inclined, you call that as isometric. The word iso means same, the word metric means measure, so it's called as your isometric projection. The next one is your dimetric projection. If two of the included angle appears to be the same between the three principal axes of the solid, you call that as dimetric projection. If none of the included angle apparent is going to be equal, then you call that as trimetric projection. And in multi-view projection, you have first angle projection, second angle projection, third angle projection, and fourth angle projection. We'll see this multi-view projection. Multi-view projection is going to be widely used in industries, production drawings, and various places where the exact dimension has to be replicated in a shop floor. Whereas the oblique projections are at times used to save time. And the perspective projection is going to be a realistic projection. Say when you want to show a building or a real-time picture, an artistic view, so you have to use perspective. Perspective is going to be a little complex drawing compared to the multi-view drawings. We'll focus now on multi-view and mostly on the first angle projection. Before that, we'll see what is that first angle. So this is about the classification of the projection. This is a table that explains like whatever we have seen earlier. The class of projection could be a perspective, parallel, in special case of parallel, an oblique, an orthographic, or an axis-based projection, or a multi-view projection. Only in case of perspective projection, the observer is going to be at finite distance, and in all other cases, the observer is going to stand at infinite distance. When you talk about the direction of the projectors, it's going to be radiating from the station point for perspective, and it's going to be parallel to each other in parallel projection, and it's going to be inclined to the plane of projection in case of oblique projection, and it's going to be perpendicular to the plane of projection in orthographic, axonometric, and multi-view projections. So now we have seen the classification of the projectors. Now this is regarding the quadrant. Now you have a quadrant. Like for example, look at this. There's a point P which is labeled in the first quadrant. The quadrants are obtained by having two planes, principal planes. The first principal plane is called as your horizontal plane, and the second principal plane is called as vertical plane. If you extend this horizontal plane beyond the vertical plane and extend the vertical plane beyond the horizontal plane, it forms four divisions, which are called as four quadrants, which are labeled here as quadrant number 1, then 2, then 3, and 4. When you consider this point P, which is kept in the first quadrant, you call that as first quadrant. It depends upon the order of the elements. The order of the element should be like this. First you need observer, then the object, then the plane of projection. If this is going to be the order, then you call that as first angle projection. And there's one more condition, that the point or the object has to be above the horizontal plane and in front of the vertical plane. So only if the observer is going to be placed such that the object is kept above the horizontal plane and in front of the vertical plane, that forms the first angle or the first quadrant. Then if the object is going to be kept behind the vertical plane, still above the horizontal plane, you call that a second quadrant. If the object is kept below the horizontal plane and behind the vertical plane, you call that as third quadrant. If the object is kept below the horizontal plane and in front of the vertical plane, you call that as fourth quadrant. So these are the four quadrants. Now it depends upon like where the object is kept. Accordingly, you call that as the first angle projection, the second angle projection, or the third angle projection, or the fourth angle projection. That is, if the object is kept in the first quadrant, you call that as first angle projection. If it's kept in the second quadrant, you call that as second angle projection. If it's kept in the third quadrant, you call that as third angle projection. And if the object is kept at fourth quadrant, you call that as fourth angle projection. So these are the four angle projections. Now there's also, so these horizontal plane and vertical plane are the two principal planes relative to which the object position can be specified, and of course observer's position can also be specified with respect to this. In case of perspective projection, the relative position of the object observer need to be specified with respect to the plane of projection. So that you called as the based on the quadrant, you call the projection. Now look at this first quadrant. So these are your horizontal plane and vertical plane and the principal planes, and the line of intersection of these two principal planes forms the reference line, which is labeled as x and y. There's a sign convention of rotating this horizontal plane. This horizontal plane has to be thought of as a single extended plane. These are imaginary planes of infinite dimensions and sometimes thought of as transparent in nature also, so that it's going to be see-through, something like a window glass. And the horizontal plane has to be rotated in such a fashion that when the object is kept in the first quadrant, then the image, the top view of the object that is going to come below the reference line, that's going to be the rotational direction of the horizontal plane. We'll see shortly about that also. Now look at this object. We are going to have the observer at infinity and the observer standing directly above and cast a ray, okay, as well as an observer who is standing in front of VP cast a ray. So the height of the object is seen by an observer who is getting the front view, and the image of the object, that is the height of the point P above the HP, is shown as a yellow color line. So this is the height what an observer can see from the front view. You can see when he sees this point, so this height is mapping there, and the point is also seen. So P dash is nothing but the image of an object or the projection of the point capital P on the vertical plane, which is called as front view, which is labeled here with the notation dash. So dash is for front view. And similarly, the observer from the top, you could see this cyan color line, and that is being transferred, and you can also see the projection of the point as small p, which is marked on HP, which is your top view. So this is how you have to obtain the front view and top view of the images. This is a multi-view, and this is also orthographic projection because the projectors are going to be perpendicular to the plane of projection. You call this as orthographic projection. And you find that we have obtained the images P dash and P, which are front view and top view respectively. And how this is represented, you need not represent this on a three-dimensional plane with such complex diagrams. We can go for a very simple sketching. So we have learned about these quadrants. Let's see about the projection of points. So draw this reference line, mark x and y, and draw a projector perpendicular to xy reference line. I reiterate, reference line xy is nothing but the line of intersection of the two principal planes VP and HP. Mark the point P dash. It's going to be a small lowercase letter with a dash or prime notation, which marks the front view of an object. Mark the height of the point above the HP. So this is nothing but the point P is 37 mm above HP, and extend the projector and mark the point in front of VP. Label that as point P and mark that height. This height is 39 millimeters in front of VP. So the point P is 39 9 mm in front of VP. So these modifiers, that is whether the point is with respect to horizontal plane, whether the point is above HP or whether the point is below HP, or whether the point is in front of VP or behind VP, has to be specified. Now let's see the projection of points, lines, planes and solids. We draw a reference line X point where we draw the top view of point A, which is labeled as lowercase letter a, and we draw the projector perpendicular to this reference line because it's orthographic, and mark off this point as A dash. We'll come back to why this A dash is within the brackets. There's a point B, then we obtain B dash. Clearly you see the point A is going to be in front of VP, the point B is also in front of VP, and they are on HP because A dash and B dash, they are marked on the line X point, they are not above. You can refer to the previous slide of this marking where you get clarity. Now you have a point C in front of VP and it is on HP, and point D in front of VP and on HP, then E in front of VP and on HP. The distances, that is the in front of distance of the point A, B, C, D, E, all are known and thus they are marked, and all these points are on the horizontal plane. Now we have already seen how to obtain the projection of a point object. Now if all these points are going to be connected in some order, okay, if there is a point O which is in front of VP, the point O is above HP at some distance, so we obtain the projection of 5 yellow dot points, and which are labeled in blue color, and one pink point which is also labeled, but the pink point is above HP. If you're going to join the line AB and BC, CD, DE and EA in order, so ABCDE is going to be a planar object, and the projection of the planar object is obtained by the front view, is obtained by joining the projections in the front view. Similarly, if the line joining the top view, point O and B is drawn, then similarly the projection, the front view of the line OB is nothing but your O dash B dash. If there is a line connecting O and C, then the front view is obtained by joining the projections O dash and C dash. If there is a line joining O and D, then its front view is obtained by joining the line joining O dash and D dash. A line connecting O and E is seen as a line connecting O dash and E dash, it's already connected, and a line connecting O and E can be seen as a line connecting O dash and B dash. Now we did not draw special lines joining O dash and A dash and O dash and E dash because we already see that the line OB and OC, they are coinciding. So that means an observer who can see the point B will be unable to see the point A because A is hidden by B. Similarly, the observer cannot see the point E because point E is hidden by the point C. So for that reason, the points A and E are placed within the brackets. Now we have seen how from the knowledge of the projection of the points, we can obtain the projection of lines, and from the projection of lines, when they are going to be connected in order, we obtain the projection of a planar object. And if any one of the point is not going to be on the plane, by joining those points to the vertices or the base points, we obtain the projection of solids also, objects also. So this is going to be an unified approach. That is, you need only the knowledge of projection of points in order to complete the projection of solids. And this is orthographic multi-view projection, because you call this as orthographic because the projectors are going to be perpendicular to the plane of projection, and you call this as multi-view because you have drawn views separately, that is, the top view of an object separately, the front view of an object separately. We'll find more views also, like for example, like you can get the image or the projection of an object in left side view, right side view. From the bottom you can obtain the image, from the back you can obtain the image. So there are 6 principal views, of which widely 3 is used, and in some cases 2 is sufficient, and in rarely some cases even 1 will be indicated. For example, when you draw a conical flask or a round bottom flask, with one of the view will be able to tell what is that object, a test tube for example. So you require only 1 view to tell what is that, you don't require even 2 views. But there are some complex objects which requires more view, 3 or up to 6 also, that depends, and sometimes it requires more views also. We'll find in later lectures how to do those things. Thank you for watching the video lecture. For further discussions, contact the following email address: kumaran.d@ktr.srmunit.ac.in.